Good day, my dear students. I hope your day was good. You are welcome to class of BCH 407, course title Biochemical Pharmacology. Today, we shall be dwelling on the topic naming, overall reaction, multiple forms of electron transport system of cytochrome P450. The focus will be the cytochrome P450 system. I am yours, Professor H.O.T. Iyawe. Before we go further, let us have a recap of Lecture 6. For those of you that have gone through the video lecture and the resource material, in video lecture 6, the focus was on biotransformation of drug, wherein it was mentioned that biotransformation converts lipophilic drugs to hydrophilic form. It occurs in phase 1 and phase 2 reactions. And this reaction is controlled by genetic, physiological, and environmental factors. It is critical for drug efficacy and safety. Now, let's get to know cytochrome P450. Electron transport system in drug metabolism are mainly cytochrome P450 systems. The systems are located in the microsomes, that is the smooth endoplasmic reticulum, inner mitochondrial membrane, where they function to catalyze oxidation reaction, which is essential in drug metabolism and detoxification reactions. Now, that said, let's look at the learning objective for this lecture number 7. The objectives for lecture number 7 are sevenfold. We are going to define cytochrome P450, explain cytochrome P450 nomenclature, describe multiple forms of cytochrome P450, outline electron transport pathways in the cytochrome P450, differentiate microsomal and mitochondrial electron transport system of the cytochrome P450, write the overall reaction of cytochrome P450, and then relate the system activity to drug metabolism. Of course, I will encourage you to have the course material, an introduction to pharmaceutical biochemistry. It will serve you right. Now, let's get started with the definition of cytochrome P450. What are they? It's a group of enzymes that catalyze metabolism of drug, toxins, and endogenous compounds. As mentioned earlier during the introduction, the functions include drug metabolism, detoxification of xenobiotics. Xenobiotics simply means foreign bodies. Then synthesis of cholesterol, steroids, and other lipids. These are anchored or mediated by cytochrome P450. What is the nomenclature of cytochrome P450? There is a standard naming protocol for this group of enzymes. Standard naming system is based on gene sequence similarity. The format is CYP, that is cytochrome P450, the family, the subfamily, and the individual. It's like us having first name, last name, or last name, surname, and other or middle names. That is the format. But you see here, the CYP 2C8 we are using as an example is a name of an enzyme. Now the format that is given up here is what is replicated here as CYP2C8. CYP, the family is 2, the subfamily is C, and the individual number is 8. Let's look at the basis of classification. Now, in considering the classification, the family is considered as well as the subfamily. There must be 40% amino acid similarity among the enzymes for the family, and for the subfamily they should be greater than 55% amino acid similarity. We must note that naming reflects evolutionary and functional relationship. There are over 300 different cytochrome P450 genes that have been identified. This arose from gene duplication, possible gene duplication, environmental adaptations to diet, chemicals, and what have you. Let's look at the functional diversity of multiple forms of cytochrome P450. I mentioned that over 300 forms have been identified. These 300 different forms have different substrate specificities. In addition, they show different metabolic rates. For example, the liver cytochrome P450 enzymes metabolize drugs, alkanes, aromatics, while in sterile tissues such as the adrenal, gonad, there these enzymes hydroxylate steroids. Now, a look at overview of electron transport system. The cytochrome P450 requires electron donors, oxygen source, and requires 2 electrons for activity. The electron donors could be NADPH or FADH, depending on the particular site the enzyme is located, whether mitochondria or microsome, as we shall see soon. This is the mitochondrial pathway in the inner mitochondrial membrane. Here you can see the NADPH donating the 2 electrons to FAD and then iron sulfur protein that is present in the adrenodosane, and the subsequent transfer to cytochrome P450. We have seen the picture. Now let's look at the components of the pathway separately. Excuse me. You can see the 4 components of the pathway: adrenodosane reductase, which is a flavoprotein; adrenodosane iron sulfur protein; cytochrome P450. These are the 4 components of the mitochondrial electron transport system pathway. Having known the components of the pathway, it is also important for us to know the electron flow sequence in the mitochondrial electron transport system of the cytochrome P450. The NADH donates electron. The electrons are transferred to adrenodosine reductase, then to adrenodosine iron sulfur protein, then to cytochrome P450. Cytochrome P450 then uses the electrons for oxygen activation and substrate oxidation. Please take note of this. Now the other pathway, the microsomal pathway, that is located in the smooth endoplasmic reticulum. Here we have also electron donor donating his electron to cytochrome P450 reductase, to cytochrome B5 reductase, and then to cytochrome P450. The cytochrome P5, I beg your pardon, the cytochrome B5 is an alternative route. It's an alternate route. So that component can be cut off without any adverse effects. Again, let's look at the component of microsomal electron transport system pathway. We have the NADPH cytochrome P450 reductase, which is a flavoprotein as mentioned earlier. It contains FAD, FMN, that is flavine mononucleotide, FAD, flavine adenine dinucleotide, cytochrome P450, which is a heme protein, and cytochrome B5, which I mentioned to you as an optional contributor. Again, let's look at electron flow sequence in the microsomal electron transport chain. Like mitochondrial pathway, NADPH donates 2 electrons. Electrons passes to FAD, subsequently to FMN, then transferred one at a time to cytochrome P450, from where it is used to reduce oxygen and oxidize substrates. What is the overall electron transfer principle in this seemingly complex system? The cytochrome P450 requires 2 electrons, as you can see in the previous diagrams, for both mitochondria and microsome or microsomal. But these 2 electrons accept only 1 electron at a time. This enzyme accepts only 1 electron at a time. Therefore, intermediate carriers are essential, and these are FAD, FMN, or iron sulfur protein. What are the basic differences between the macrosomal and the mitochondrial pathways? Now let's start it with the feature, the macrosomal pathway, the mitochondrial pathway. The macrosomal is located in endoplasmic reticulum, while the macrosomal is located in the endoplasmic reticulum, while mitochondria is located in the mitochondrial compartment. The enzyme moiety is, for macrosomal pathway, NADPH, cytochrome P450 reductase, while the mitochondria is adrenodosine reductase. The carrier for macrosomal is FAD-FMN, while the carrier for mitochondrial pathway is iron sulfur, that is adrenodosine. The extra components, which is optional in functionality, is cytochrome B5, whereas in mitochondrial pathway, none exists. In terms of function, the macrosomal pathway is involved in drug metabolism, while the mitochondrial pathway, the function is strictly for steroid synthesis. This is the overall reaction equation for cytochrome P450. Redox reaction when NADH is oxidized and oxygen is reduced. The half equation is presented. Of course, the full equation is coupled to ATP synthesis. At this point, we can ask ourselves, what is the relationship between cytochrome P450 activity and drug metabolism? The relationship are as follows. 1. Cytochrome P450 enzymes are primary drug metabolizers. They catalyze phase 1 oxidation reaction. In doing so, they convert drugs into water-soluble metabolites, which is easy to excrete through urine or bile. Number 2, cytochrome P450 controls drug clearance. When there is high cytochrome P450 activity, metabolism is faster. Drug is cleared quickly from the system to reduce the drug effects. However, when cytochrome P450 activity is low, it will result to slower metabolism, and then drugs accumulate, thereby increasing the risk of toxicity. Number 3, cytochrome P450 and drug activation, that is, prodrugs. What we mean by prodrugs are the drugs you take in, and those drugs are on their own, in their natural states, inactive until acted upon by enzyme to make them active. Some drugs are inactive until metabolized. Cytochrome P450 converts prodrug to active drugs. Number 4, cytochrome P450 isoforms determine specificity. Different cytochrome P450 enzymes or different cytochrome P450 metabolize different drugs. For example, CYP3A4, CYP2D6, CYP2C9. These are different forms of cytochrome P450. A single drug may be metabolized by more than one form of cytochrome P450. Drug metabolism depends, therefore, on which cytochrome P450 is present. I mentioned this before. Genetic variation, where individuals differ in cytochrome P450 expressions. Number 6, we have drug-drug interaction, cytochrome P450 inhibition and induction. In the case of inhibition, one drug blocks cytochrome P450 enzyme, and that blockade can result to reduced metabolism of another drug and then result to drug accumulation, which in turn becomes toxic. For cytochrome P450 induction, one drug can increase cytochrome P450 enzyme synthesis. Such action can result in faster metabolism and reduced drug effectiveness. Cytochrome P450, number 7, determines drug half-life, as it is able to influence duration of action as well as dosing frequency. High cytochrome P450 activity is equivalent to short half-life, while low cytochrome P450 activity results to prolonged half-life. The number 8 is the overall reaction link. This was the reaction presented earlier in the course of our discussion or in the course of this lecture. You can see that oxygen is introduced to increase polarity to the substrate. And this is the phase that prepares the reaction for phase 2 conjugation reaction for excretion. Now, we started this lecture by having a recap and also introduction, a recap of lecture 6, introduction to cytochrome P450, nomenclature of cytochrome P450, definition, multiple forms of cytochrome P450, electron transport system of the cytochrome P450, as well as the pathways in both mitochondria and microsoma. We talked about principle of electron transfer, and we now compared microsomal electron transport system with that of mitochondrial electron transport system. We also looked at the overall reaction of cytochrome P450 system, and we are concluding with cytochrome P450 activity and drug metabolism. Again, as usual, I have a set of questions here you can use to help yourself to test your level of comprehension or otherwise of what has been presented. Take your time to tease yourself and do it sincerely and faithfully. We have come to the end of this class, lecture number 7. I want to thank you for your time. God bless you.